right, we're gonna get started. 8:30 sharp. So good morning, everyone, and welcome to the last day of the Dev Summit. So how the whole week has been for you so far? It's good? You learn a lot, I hope. So just to check the audience, how many of you are developers? All of you or not? Okay, most of you. So how many of you are JavaScript developers? Almost everybody. All right. How about .NET? So you do both .NET and JavaScript and Python and C++ and everything? Okay. And Java, of course, yeah. I think these days developer has to do a lot of different languages. So no end to it, which is good news and also bad news to us. All right. So I've been here with Esri for, this is going 21 years already. So I started in 1996 with the 3D. At that time, we didn't have 3D team yet. So I came with my PhD research was about 3D GIS. So I joined Esri in 1996 and has helped setting up the 3D team. And then I also did a few things in 3D. Start initial development of ArcScene, for example, and then involved in a number of things for ArcGlobe and simulation in real time. So my current role is I work with the professional service with Adam. So Adam is leading up our real-time GIS initiative and development. So we have a number of development projects. So my interest sort of transition from 3D to 4D. So I add 1D to my journey, right? So I think not too far in the future, we're going to have to do a lot more work in real-time and 3D. We have a lot of initiatives, many cities and countries talking about smart cities application, for example, and smart cities need 3D and also real-time data from sensors. So this is why we like to keep 3D and real-time together. So agenda for today, I'm going to talk briefly about 3D for ArcGIS and then real-time, and touch a little bit about static 3D scenes. So how many of us are really doing work in 3D? So we're going to have a lot of talk about that right at the end. So how many of you are just thinking about getting into 3D? All right, okay. So static scene has been developed since, I would say, since I joined Esri, and has been advancing until now. And we start seeing real-time rendering in 3D scenes, and we see a lot of development from desktop into web. And the web 3D is something that we would like to have for a long time. People have been asking for that, but we still address mostly static 3D scene, even with the web. So last couple of years, we start looking at real-time with 3D and also real-time with 3D in the web, not just the desktop. So today, focus will be mostly with the web, okay, 3D with the web in real time. We could do almost everything with desktop already, right? Yeah, but the web is the remaining challenge. That's why I like to focus on that today. We like to see from the static 3D scene that we have, how to make it become alive. Well, you have seen a lot of static scene. I know you have seen the gaming stuff, which is very dynamic in 3D, but in the GIS domain, we don't see too many dynamic and scene just yet because of some limitations. So looking at our 3D map or 3D scenes, if you use the goggles, and you're really immersive into that. You walk alone into the city, it's kind of lonely, right? So we want to have some life in the 3D scene. I will talk about real-time 3D visualization, some technique, some considerations, how to keep up with live data and performance. So that's be something we need to discuss and be aware of. How can we tune our 3D scene, which is in the static 3D scene is not so much problem. But when you start adding dynamic data, especially if it's high volume, high frequencies, then that will be a big challenge. So our 3D has been advancing, and we now not just having ArcScene and ArcGlobe anymore. We have ArcGIS Pro, which merge scene and globe and 2D into one application, but it's still desktop version of that. We also have ArcGIS Earth, which is using for KML visualization mostly. So Google Earth, and now we have ArcGIS Earth to fill the gaps that Google has stopped supporting, I think, the enterprise version of Google Earth. So a number of users that use KML data still need it. So Esri stepped in and developed ArcGIS Earth for that purpose. ArcGIS Pro is a desktop version, and it's the native Windows. So it uses OpenGL heavily, and it's advancing to use a number of advancing OpenGL renderer in 3D, and it's also doing 2D as well. So you could have both 2D and 3D scene at the same time. In the past, when I started prototyping ArcScene, there was many questions about should we have both 2D and 3D in one applications, and we discussed that for almost a year until I decided to, okay, let's just do ArcScene separately so that we sort of have its own path for now, and then we have ArcScene as a product. But more and more that people start using ArcMap and ArcScene together, they're seeing a lot of similarities in terms of managing document and scene and map. So people start asking, can we have the same experience, user experience in just one application, so we don't need to keep switching between applications? So that's why we start looking at ArcGIS Pro, try to merge 2D and 3D, scene and globe view into one, right? So you have three things. In Pro, you have 2D map, you have scene, which is local, good for city level, for example. And then you have global scale, globe view, right, at the same in the same applications. So you can transition from 2D to local scene, and then you can look at the global scale at the same time. This is important because in real-time and tracking, real-time monitoring, sometimes you have to deal with application that not just in your local area. For example, you track flight or chips. Sometimes that you have to go across many cities, and you go to a continent and global scales. So we should be able to transition from local to global. And then we start having the web versions. People have been asking, okay, I don't want to install application on my desktop. Sometime in the defense domain, install something on your desktop, need to have a lot of security check and certification, things like that. Sometimes it takes really long time to just install application in a desktop for in that domain. So we start to look at 3D control in the web. It didn't work well, it needs plugins. The advent of WebGL allow us to do 3D visualization in the web within the browser without running any plugin at all. So that's good news, but the performance and the capabilities of the WebGL is still advancing, is still catching up with OpenGL. It's not as powerful as a desktop. From my experience, we can do a lot more in desktop still, and the web still catching up. Okay. Anyway, it's good for us to start looking into that no matter what, because it's going to get better and better over time. We also have the runtime SDK in case you want to do custom development. The SDK available for Windows, iOS, Android. So mobile device can also have 3D. So the application level, when you look at the entire architecture, you could see that to support those applications, we have to have the backend architecture or platform to support it. And we have the entire ArcGIS enterprise from GeoDatabase, ArcGIS server, portal, ArcGIS online, and something new is coming as well into that area. RealTime is also part of that the platform solution that we provide to feed all the application with data, real-time data. So the web scenes, I'm going to talk, focus on the web. So that's why I have the web scenes slide here. Web scenes is like a container. It's like in the past we have MXD and we have SXD, we have Globe document. I don't remember the extension anymore. In the web scene, in the web we have web scene as a container for that, and the web scene contains scene layers. These layers can come from different sources. Remember that layers is a abstraction for data, right, with renderer. So data plus renderer become layer. So you need to have renderer with the data. And you can change different kind of renderer. If you remember or recall some of those, like single symbols or unique values, color ramp symbols and stuff like that. In 3D, those symbols could be 3D models, the whole 3D models of something like aircraft or vehicles, or even windmill, for example. We're going to see some windmill today in the demo. So web scene has seed layers, and seed layers composed of graphics and attribute, geometry attribute, right? And the attribute is something that will be used for rendering. So in real time, when you feed the data in real time, the attributes might be changing over time. So the renderer has to adapt to that change of attribute appropriately. And we're still working to get there with the web version of 3D visualizations. So we support point light polygons. We support meshes, support point crown, and some of the image texture. So this slide is just showing that we have 3D across platforms, desktop, web, or device. But if you program it in something like JavaScript, it will run across those platforms because it runs in the browser, right? Be aware that some browsers still not supporting OpenGL that well. So there will be problem with some device. So you have to expect some of that problem. iOS, Android, most of the Chrome browser supporting WebGL already on desktop and on the device as well. Our API is still catching up on that. We have a code that detects if WebGL is supported in the browser. So when you start running the applications, it will detect that. And if the web browser doesn't support WebGL, your application will not run. But sometimes that check may not be totally correct because you use Esri API and it say, oh, WebGL, you are using this version of browser, it's not supporting, but if you run some other WebGL, it's working. So expect some discrepancy on that until our API catching up on variety of or version of browsers. So the entire product family of 3D look like this from Pro, and this is more a desktop applications that help to manage content and authoring. You can authoring scenes and then publish to scene service, web scenes. We also have 3D analysts if you want to do analytics with 3D. I would say that our 3D functionality is not yet really volumetrics. Okay, it's still a lot surface based or 2.5D. We are working on volumetric analytics function, which if you talk at the level of 3D raster, for example, or voxel, we don't have that yet. It doesn't mean that we cannot build it. It's just a matter of how many people want it, right? And we're not sure about that yet. We have realistic 3D visualization, city engine. Esri bought city engines several years ago and start integrating city engines into our 3D product family. City engines was cinematics, 3D realistic rendering used in a number of movies like Cars, for example, animated movie. I don't remember what else that being used with city engines, but you could see that we were looking for a really realistic 3D rendering engines, and at that time, Esri didn't really have expertise to do that at that level. We could do 3D rendering, but realistic scene with high performance was a challenge to us. That's why we decided to just go out and purchase, what people, the product that already available that we can integrate into GIS. So since then, we have been integrating City Engine with GIS, and it still have a lot of work to do. It's still not seamless. It has a lot of differences. For example, the way you program against City Engine, you use its own scripting language, right? When you program in ArcGIS, you use .NET or you use JavaScript. Now, how to merge the two together, it's questionable. So a lot of work still need to be done. The dream is that if we could have all the GIS data rendering in City Engines or bring City Engine data into GIS, that would be fantastic, but that's still something to be done. On the ArcGIS server, we have all the extensions to support that. We can publish 3D content, 2D content. And ArcGIS Online start to already support some of those scene management. We have ArcGIS Earth, I mentioned, we have RealTime, and we have some third party. So comparison between 3D RealTime SDK and the JavaScript versions. So you can look through the list here, and it mentioned that the SDK support larger data set, and it's using machine native code. On the JavaScript, you have to go to the layer of translation away from JavaScript, and from JavaScript to OpenGL, to WebGL, and to OpenGL low level. So there are some steps. That's why it may not perform as good as native code. So keep in mind that if you want to do development, you have to make some hard decision here if you want to make it easy for the user, but the trade-off would probably be the limitation in terms of how many objects you can handle in the scenes and the frame rate that you would get in how smooth the rendering could be. I will show you some of those problems today. The good thing about if you use JavaScript, you have just one code base that runs across the platforms. You use native code, of course. Now you have to be native to what? To iOS, native to Android, you have to be native to Windows. Now you have like 3 or even more code bases to manage, right? And they are slightly different, or some might be a lot different. JavaScript 4.x, that is the version that starts to support both 2D and 3D. If you're using JavaScript 3.x, you can't do 3D. Okay, you have to write your own custom code for that. But 4x, we have integrated WebGL into that, so we can do 3D. So having 3D doesn't mean that you can use real-time data. So this is the part that we're still working to get the real-time data supported by our API across the board. Not just the JavaScript API, but desktop SDK, inside the dashboard, inside of ArcGIS Earth, for example. Everything we need support for the real-time layers. So our real-time layers, what are those? One of them is a stream layer. Stream layer is coming from GeoEvent stream service, and it's supported in JavaScript API since 3.x. Okay, but you can render it in 3D. But in JavaScript 4.x, you can render the real-time stream layer in 3D. KML is another source. How many people are still using KML? Okay, so it remains supported. The KML that we support, GeoEvent can publish real-time data into KML to the so-called network link update. Okay, network link update is a callback. So you start off with Bootstrap KML content. It may have lists of features, right, or objects with the network link that will call back to the server, and the server will push data. Or actually, the network link is more like polling for update from the server. So it's not a real push. It's still callback polling to the endpoint that the server provided. So server have to provide an endpoint that can update the content, and then the network link will come and pick it up. And the rendering of KML, whether it be Google Earth or ArcGIS Earth, will pick up the change and then rendering accordingly. I start listing feature service. From my last year presentation, I didn't have feature services as part of supporting real-time data. And you might ask why. The reason was, back then we used traditional relational database, and the performance was not enough to support real-time. You could do polling on interval, but to make a smooth or high rate data reading or retrieving from feature services, it couldn't satisfy the 3D visualization, especially if you need to have a really high frame rate. 3D visualization needs frame rate to be more than at least 24 frames per second. Kind of like movie, right? Movie is 24 frames per second. But if you want to really have a smooth, rendering that eye-pleasing to the user, otherwise user will have motion sickness and stuff like that, symptom after looking at the low refresh rate. So you want to have 60 frames per second. If you're looking at that in stereo vision, right, you need to have at least 120 frames per second. Otherwise, people will come out from your session and start to have nausea and stuff like that. Yeah. So if you go to the theaters with 3D movie, or your televisions have 3D goggles, you should look at least 120 frames per second. And they have 240 frames per second as well. So that the display requirement. Our feature services from Spatial Temporal Big Data Store. This is coming from Elasticsearch as the basis of that component. Have a really fast writing rate. Either you do add, update, or delete it really fast. You can write tens of thousands of features per second to that database. It's not traditional database like Oracle or SQL Server. It is NoSQL. And heavily used in memory cache. So Spatial Temporal Big Data Store will require you to have a really strong hardware in terms of RAM and hard drive, storage volume, capacity. It has a very rapid retrieval rate as well. So you can retrieve millions and millions of records back in a few seconds. So you can repeatedly request, hitting that REST endpoint feature service that coming from big data store, and the data rate could surpass the stream layer. Stream layer is capped at about 3,000 events per second, but when you can retrieve millions of features back from an endpoint of spatial temporal big data, now you can question, okay, I'm surpassing 3,000 features per second or not. Sometimes I would say you do, right? And if you have millions of records, then the question is how you render them in 3D. That still can keep up with performance. So real-time JS is what we would like to say that this needs to be integrated with 3D, and the advent of Internet of Things amplify the size and the volume of data, the frequency of data, everything. So I had a IoT sessions on Tuesday, and one of my slides have the statistics of we are approaching 75 billion objects by 2020. So probably we have at this point 40 billion maybe, and imagine if we need to bring those data in, just some percent of those billion, right? And render in the 3D, render that in smart cities. You know, you have all these 3D buildings already, and then in every room, every floor, you may have temperature, for example, sensors, and you want to display which room getting hot and stuff like that. And imagine that if you have a lot of sensor and a lot of room in one building, and how you render that, right? And those are just static sensor. But talking about moving objects, then it's even more challenging. It's a kind of good problem to have. So our real-time JS could do some spatial reasoning. We could do real-time analytics. So when we receive data from sensor, we do some sort of analytic already, and then we do detection, alerting, and send output to feature service or emails or SMS or whatever. We can even send tweet. When we send to feature service or stream layer, stream service, this is where you want to tap into to bring the data into 3D and render the data. So this is just some introduction for real times. So we are dealing with space-time change over times. We're dealing with tracks, meaning that observation come to us one by one, and you have to have a way to correlate them into an object, right? So that you know you can form a track of objects that move over time. If the object doesn't move, you don't form a track, but you have an object with change of attributes over time. The slide to the right is just like if you already form the object over time, then you can play it back over time as well. So this is what we call temporal data, right? It's like a film strip or the video clip that you recorded and you want to play back. And you could see a person or actor and actress, objects in the scene moving around, and you still can recognize them, right? So that's a track, and you can visualize it as space-time 3D XYT in some case. So look at the architecture of this that will support real-time. So it's something called ArcGIS Enterprise. So the product name marketing-wise keep changing, so you have to keep up with that as well. So what's in the ArcGIS Enterprise? GeoEvent Server. Now it's called GeoEvent Server. It used to call GeoEvent extension for ArcGIS Server, but now we shorten the name to make it easier to call GeoEvent Server. GeoEvent Server is down there on the bottom left with purple color. And we have introduced Spatial Temporal Big Data Store in 10.4. The reason to do that, I already gave you the reason, because the relational database couldn't keep up with the incoming rate. So we have a lot of backlog sitting and waiting to write to the database, and people start complaining, I got my vehicle sent out the data and it was here 5 minutes ago and I don't see it show up on the map yet. What's going on? It's because the relational database couldn't keep up and we have a backlog of data in memory that's waiting to write to the database. So we start to develop, we're looking for new solutions. We introduce spatial temporal big data. We're looking for a much faster writing rate for that, and then this is what we come up with. Someone will say maybe Hadoop or something, but this is not Hadoop. This is Elasticsearch, okay? Elasticsearch, you see the symbol as rings and have 5 nodes in there. The nice thing about this spatial big data, spatial temporal big data is you can add more server to it to scale. So if say one instance is not enough, you can add more nodes to form its own cluster, mini cluster. And it will start distributing data across those nodes automatically. You don't need to do anything. This is done behind the scene. It auto scaling, it's auto replication, and fail-safe. For example, if one node went down, data would be rebalanced automatically to the remaining node. Okay, so that's a nice thing to have. Also, when you write a piece of data to a node, that node will make sure that it has another copy on a different node, so that in case it went down, the other one pick up. Okay, so you don't lose data. I would suggest that if you're not using the big data, our spatial temporal big data yet, play with it, and you will agree with me that it might be a game changer for GIS. So once you write the data into big data store, question is, what do I do with it, right? What can I do with it? So spatial temporal big data automatically publish a feature and map service. So it will hand you back feature JSONs and mapped image map tile. So we have a server-side rendering for big data. We do automatic aggregations of data as well. When you render, say you have, I recorded, I think for 2 weeks or 3 weeks already of flight data from the whole world. And I have now about 100 million records in my spatial big data store. And you can imagine to render that amount of data on the client side, you can imagine that, which client can do that, right? So we start looking at server-side rendering, especially when you have to do aggregations. Server-side will render that for you. But if you want to get to individual data, we have feature service that you can get to features, not just the image map tile. In 10.5, we introduced GeoAnalytics server. GeoAnalytics is very much, you can imagine if you're familiar with geoprocessing, it's analytic component for GIS, right? GeoAnalytics is working on big data. It can work with big and small, but it's targeting big data, okay? So it will read from our big data store and do analytics. In the first release, it probably have a handful set of analytic functions, not as rich as geoprocessing yet, but we will start migrating a lot of those capabilities onto GeoAnalytics in the future, so make it rich functionalities. So this part is still evolving. So this is just to show you the rate, you see the number. In 10.4, we managed to reach 4,000 events per second on the ingestion to GeoEvent. In terms of visualization, we used to say that, okay, the stream, since it's the most performing piece, then the visualization also keeping up with 4,000 events per second. If you in web map, you might notice that when you start to exceed 3,000 or 4,000 graphic on the screen, it starts to choke, right? It starts to drop out some of graphics elements. So you don't see everything sometimes. Yeah. So that will look like a limitation on the web still. On the writing, since we introduced the spatial temporal big data, 10,000 of events per second can be written. This is not the limit. You can still scale it up beyond that. Remember when I said you can add rings, you can add VMs, new VMs into the ring, and that will even increase the performance, the capacity. So you can go beyond 10,000. So it allows to scale up or scale out. Come back to the same question, you scale the data, that's good, but how can you render them? So this piece will remain a challenge. All right, this one I'm not gonna talk too much. I believe you know the static scene pretty well. And I already mentioned that data can coming from multiple sources, right? Like geodatabase or CityGML. But we also have data coming from real-time GIS platform right now, like GeoEvent. Those will still become feature layers or stream layers. Stream layer is not listed here, but those will be part of the scene layers and scene service. Actually, I would say that most of the real-time layers wouldn't be part of the scene service. Scene service are pretty much static scene, okay? So the container at the web map or web scene level will allow you to add the stream as a layer, but you won't publish that as part of the scene service. So to make your scene come alive, you have to bring in real-time data. And I mentioned before that you could bring it into the scenes in two ways. Actually, there are more than two ways, I would say that, but in our platform, we have two for now. The first one would be from feature service or map service. So feature service means that you want to do client-side rendering. You have to pull from your application back to the feature service endpoint to get the data back in feature JSONs, and then our API will deserialize JSON structure into features and graphics, and then render that inside the scene. So this is a polling or pull approach. And then we have streams. Stream, the underlying technology for stream is WebSocket. WebSocket is pretty much TCP connections. Okay, but first you make HTTP connections, and then behind the scenes, it will upgrade to TCP connections, and will keep the connection alive, as opposed to HTTP. For HTTP, when you make a request for data, you get data back, and then the connection will be disconnected, right? If you want data again, then you open connection, make connection, request for data, and get data back, disconnect. You can keep live connection in HTTP. We have something called long polling. For example, you get data from Twitter Firehose, for example, you get HTTP long polling, meaning that it keeps the connection alive, and it keeps pushing data to you. So I'm not saying that HTTP just, get data and disconnect all the time, but in some cases, special cases, it can keep data alive. However, that doesn't seem to be a good way to keep connection, because you still have to request for data. For WebSocket or stream layer, we make connection, we subscribe to stream, and then once the data available, it pushes data from the server to the client automatically without going to any database or persistent layer at all. So bypass everything, okay? As opposed to the feature. Feature have to go first to the database, and then you will query that from the database. What the advantage and disadvantage of that? If you use feature, you prevent data loss because you already persisted in the database, right? And then the application query, it could go back in time to get historical data previously. Let's say you get data this time and your network get disconnected. You don't get the data come back because network interruptions. So you say, let's try again, go and try to get data again. And the network restore. So now you can get data, right? For stream, it's a push, it's a file and forget. So server, you make connection to server, you say subscribe. When data arrives at server will push it directly to the client. If you have network interruptions, server still try to push and then the data loss. The client wouldn't get data. There is no handshake or notification, confirmation of data receiving. We have not implemented that yet. So remember that if you see data loss, it could be, if you use stream, it's a lossy approach. It's fast, but you can lose data. Server send out data and totally forget about it. I sent it already. I don't care if you get it or not, right? Yeah, so that's a stream. So asking which one should I suggest you to use? I would say sometimes I do both because the stream update is instant. When you send out data, the client will get it right away. If you go through feature service, you get some latency, maybe a few seconds or a few 100 or 200 milliseconds, depending on how far are you from the application to the server. Right? If you're pretty much local, it will be faster. However, with the advent of big data, spatial temporal, that I say again, the performance come close to stream, and you also don't lose any data. Okay, so that's why I suggest to play with it. So this kind of demonstrate what I just said. All right. I talked already a lot about the stream layers. I don't need to go through that details. It's available since 10.3, and we are in 10.5 right now. It's also managed by Portal as well, so you can restrict access to stream layer if you use Portal. I'm going to show some demos. Let's see if I need to switch to something to make that happen. Okay. All right. PowerPoint is getting very smart now. If you try to exit from its presentation mode, it won't show my screen. So I need to exit the entire thing. This is GeoEvent, and you see the data that's coming in. GeoEvent sample 3 Esri.com. This is on Amazon AWS EC2 machines. This machine is a VM of 32 gigabytes of RAM with 16 cores. We subscribe to a FlightAware Firehose. The FlightAware Firehose stream data from FAA and ADSB receiver and radar. They aggregate the feed and give us a feed for research and development and also some marketing purpose. And you could see that data come in at peak of 356 events per second, but it pushing out in different channels. The FlightAware data come in with multiple data types. So they have flight positions, flight right now in the air, flight plan, meaning that before the flight took off, they have to file the flight plan to the FAA or air traffic control first, so they know where are they going, which route they're going to take. There are flight arrival, flight departure event, flight cancellations, things like that. There also we also have activity on the ground as well. I will show you some of those. Let me see here. Okay, this might be a good one. So I show you in the 2D first, so you have some idea about real-time data. How does it look like? Hopefully we have a good network. Not what we got. Let me try again one more time. If it's not working, I'm going to show you the video. Or in the meantime, I can just skip to the video because we have just 15 minutes left. All right. See, that's a vehicle. So one thing to know about is the operation dashboard doesn't support stream layers. This is why in the first part of my talk saying the entire Esri teams, development teams, they need to catch up with supporting real time even more, right? And that's coming. So how do I make this work and still, you could see that the plane movement and everything is seem to be pretty smooth enough, right? And this is the activity in Los Angeles International Airport. So the video will show you, okay, from zooming out, what is the area. The flight-aware data feed provide these kind of data across the world. So most of the major airport at the ground level activities, we have that data, and it's coming in at the rate of about 1,000 events per second, or even more at the peak time. The activity on the ground include flight, taxiing, taking off, and also all those baggage trucks running around the shuttle. And if you're in LAX, you can tell that the shuttle that run between terminals along the side with the aircraft, right, taxiing. It's kind of interesting. So I can zoom into different locations in the world and see the activities. And now you can start imagining if you are in the business of working with the airport to show them in 3D, the flight coming, taking off and landing and all the activity on the ground. If they want in 3D, what you do, right? This example of data. So since the dashboard doesn't support stream, I have to use big data store. So this is the performance you're seeing when I'm retrieving data from big data store. Inside a big data store, there probably be millions of records because this data covers the entire world. And you could see that I can click on any of those and get attribute quickly, right? If you use a lot of relational database, and if you pass, I don't know, 500,000 million or something, you try to load that into ArcMap or ArcScene, and you can tell what's going to happen. You sit there and wait for 15, 20 minutes, and at the end it crash, right? So this is why we try to get. You see that when I do a selection, it flashes the entire screen, meaning that it has to go through all those objects, right, so that it can render the animated highlight. All right, and then all the statistics on the right-hand side and things like that. Now, if we want to have 3D dashboard, it's like, okay, how do we do that? So I'm going to go back in the past a little bit. So this was the desktop version. You can tell this is ArcGlobe, right? I did this in around 2005. So all the 3D airspace, the file restricted zone are extruded as polygons. And the 3D flight models are loaded. That time I used just one flight symbol. And then we render the stick so that you kind of project the position of aircraft onto the ground, and you have to keep that moving also. Back then it was tracking and stuff like that, but we could do pretty much almost everything we want back then. You could see a lot of flights in the full 3D models. And with the dynamic weather coming into the scene as well. So that was desktop a long time ago, and if you want to do the same in the web versions, can we do that? Another symbology that we could do back then, around the year 2005, is rendering high detail level of details. So I'm going to skip really quickly. So we have 3 objects in there. This is arc scene. This was arc scene. So you need to render really detailed object like trees. You could see the leaves is really realistic leaves here. And the engine, there was a company in Germany that doing this plant rendering, plant modeling. See the twig and leaves are really nice. Even that detail, right? These are millions and millions of polygons and texture polygon to be rendered. So it needs a very sophisticated engine to do that. It needs to be able to adapt different level of details, mapping onto really detailed geometry, millions and millions of polygons to be rendered. So if we need all of that in our scene, can we get there with our WebGL? So I'm gonna show you the web. Okay, this is another one. Not go to the web yet, still back in the past. So this is what we could do with the RealTime SDK, right? So we could bring in the map controls and the globe control in the inset, and then the bigger one with the more details. You may ask, what is this? And you could see at the header saying Euro flight landing guidance. So I had a project with, I think it was European communities with University of Munich. They tried to put in flight landing guidance into a smaller or medium aircraft in Europe, try to cut the cost, because the current guiding system costs about 10,000 euro or something, and they're looking at if we can make it within 5,000, cut the cost in half and put this in the cockpit. So when you're flying and you need to land, and suddenly you have bad, environment, you couldn't see because of snow or foggy. Now you still need to land because you don't have enough fuel to fly anywhere else. What you do? So they want to have a guiding system with the corridor, and the pilot just try to follow that, and then at the end, hopefully he land safely, right? Even if he couldn't see, but visual. So there's a landing tunnel, and it fitting in real time from the flight equipment, inertia system and GPS. So the pilot try to control his aircraft not to get out from the tunnel. If he veer too much, then it gives you alert and say, come back. Try to keep inside the tunnels, something like that. And he can select approach tunnel. So we have all that. So I'm going to show the landing moment. So all this was done in the desktop version. There's an agency in Europe that's starting this for web now. And they probably will open up for public access soon. So from this prototype now, we have a web version, which I cannot show to you, unfortunately, because they're not ready for that. Okay, but I have seen the version that look really similar to this. But it's running inside of the browser using JavaScript API and our or the enterprise JS platform. So you could see that data is pretty important. We cannot have runway that going like that. So you see the accuracy of data, right, when you come close to this. Look at the runway, meaning that our digital terrain model is not that accurate, especially this part. Oh, I just skip over. Here it is. That you could see that it just dropped. You can't do that. And in this scene, we do have 3D buildings as well. Okay, I'm gonna try to skip over. So that's the airport facilities with all the texture map things on the left. Yeah. Okay, I have 4 minutes, so I'm gonna show you some of the rendering in the web that we have at this point. So compose. We have a lot of these sample code on the web as part of our JavaScript 4 APIs. So I probably won't show you the code on the interest of time. Let's see if we get connection. Hopefully we see some object here. Okay, here it is. So this demo is using the windmill symbology, and if you are familiar with the term instancing in 3D, so it used one model and do instancing, replicate it on different locations in the scenes. If you notice, the windmill is moving. They are moving based on the current location from data streaming into stream layers, and then coming into the scene layer here. And the propeller of the windmill rotate, I believe that using the ground speed of the aircraft. So it kind of, it's not the way that we should represent the aircraft, but I want to show you that you can use different part of your model to signify the attribute value, right? Actually, to be good, the height of the windmill is supposed to be according to the flying height. That would be cool, yeah. But I have some difficulty to make that scale, so I just present it. But you could see that, a lot of windmills here. This is for the entire US. If I zoom out, if I can zoom out. Okay. Yeah. Try to pan. See if I can touch it. No. So this is the data coming from FAA that we capture, and it covered the entire US airspace. So there are a lot of them, right? This one using, is a WebGL rendering. Now, it's a direct WebGL. The other one I rendered using Tree.js. If you know, Tree.js is one of the 3D rendering engines that are very popular right now. Pretty powerful and easy to use. So we have a real-time 3D flight. Let's see if it's gonna work. So we're at the mercy of the web. Okay, here it is. So you see those three axes. It's the location of the flight. And if you, okay, I'm gonna wait until all the texture come in. All right. If I zoom close, now you see the full 3D models of the aircraft. Also with that billboard rendering, right? So this one employed the use of LOD as well. For example, if I zoom out far, you could see that I don't see the full model of the aircraft anymore. I only see the axis, right? So I have a distance LOD by distance checking. I have 3 distance of LOD. If it's very far away, I have a smaller, you see over there, very small axis. Come a little bit closer, I have a longer range of axis to display. I don't display the full 3D models. When I come really close, then I display the full 3D model of the aircraft. You see aircraft is not flying, so I can turn on the predictive mode. The predictive mode calculate the heading and the distance to move in the next positions in every cycle of screen update, so it moves every time. So if your screen update every 60 frames per second, so this will be like 60 times it moves, okay? Because it's every cycle. The tricky part of implementing this is you have one thread of receiving stream data coming in really quickly, and you have another thread of rendering, and how you synchronize these two together is a challenge, yeah. So all right, get back to my PowerPoint to wrap this up. So, okay, I think you see that? Jump to the conclusion. So we have all the elements that are ready to do real-time 3D. We can make our scene become alive, as you have seen from my example. We're still working on performance, and this is on the mercy of the WebGL as well, because that's part of the browser that we have no control over it. So anyway, if you want to provide something like this in the browser, it's probably a good time to stepping in to catch the start and show the moment. It will be performing better in the future. And okay, I have that. So I want to build a holodeck. You can walk in there and you have all the 3D rendering and sensor real-time data, and you can enjoy, virtual environment at some point. So okay, that's the end of my talk. Thank you.